Hey guys, taking a look here at day one of 6-3. We'll split this again into a couple days. I'll split the homework up into a couple days for you, but I do want you turning this in all as one assignment on Flipgrid, but we'll worry about that next week. So we're talking about this thing called binomial radical expressions. Basically, what we're looking at is how to add, subtract, multiply, divide with radical expressions. That's basically what we're looking at. I think this is way too complicated to call it, but that's what your book called it, so that's what we're going to call it. All right. Before we get going, we need just one quick definition here. What like radicals are, and it's real similar to like terms. All right. Like terms are terms that have the same the same variables and the same exponents. Like radicals have the same radicand and index. All right. So if we're talking about like radicals, those are two radical expressions that have the same radicand and the same index. All right. So just a couple examples. 3 square root of 5 and -4 square root of 5 are like radicals because they've got the same radicand. All right. 5, and they've got the same index. They're both square roots. All right, so these two would be like radicals. All right, a couple non-examples would be 3 times the square root of 2 and 3 times the square root of 3. Those are not like radicals because they don't have the same radicand. All right, so I'm going to put an X through there just so you don't get confused. Another non-example would be 5 times the square root of 2 and let's say 8 times the cube root of 2. Those are not like radicals because, yeah, they've got the same radicand, but this is a square root and this is a cube root. They don't have the same index, all right? So in order to be like radicals, we have to have the same index and the same radicand. All right. And so to combine radical expressions, like I said, today we're going to look at sums and differences, addition and subtraction problems. All right. We can only combine radical expressions if they are like radicals. That's the only time we can add and subtract radical expressions is if they are like radicals. All right. And we're just going to look at some examples here real quick. There's probably some more definition I could give you there, but I'd rather get on to the examples. So it says, what's the simplified form of 3 times the square root of 5x minus 2 times the square root of 5x? So again, first question we have to ask ourselves is, are they like radicals? Yes, they are. They have the same radicand, 5x, and they have the same index. They're both square roots. And, just like we would do, now again, I'm going to just step off to the side here. If I gave you 3y minus 2y, you would combine these by, in this case, subtracting the coefficients, all right, and you would get 1y. It's really the same thing here. In place of y now, we just have the square root of 5x. So I can combine these, since they are like radicals, by simply subtracting these two, let's call them coefficients for lack of a better word, all right? So it'd be 1 times the square root of 5x. Or you simply could put the square root of 5x, just like here. A lot of times we don't write that 1, we just say y, all right? This, again, putting the 1 there is not a mistake, it's not a problem, but it's not needed. All right, here, if I look at 6x squared times the square root of 7 plus 4x times the square root of 5, I can't do anything because these are not like radicals, all right? So this is the simplified form of that, okay? Here, I've got 12 times the cube root of 7xy minus 8 times the cube root of 7xy. They are like radicals, same radicand, same index, so I can simply combine by doing 12 minus 8, and I get 4 times the cube root of 7xy. All right. So adding and subtracting like radicals is just like adding and subtracting like terms. All right. I know the two we did were both subtraction, but if this would have been an addition sign here, it simply would have been 20 times the cube root of 7xy. All right. Now, just one quick example here, all right, of kind of applying this a little bit. There we go. It says, in this stained glass window design, the side of each square is 5 inches. Given that the length of the diagonal of square with side x is x times the square root of 2, find the perimeter of the window to the nearest tenth of an inch. All right, so wait a minute, what are they talking about here? Well, perimeter is distance around. All right, so we just want to find all four sides here and add all that up. Well, how can we do that? Well, they tell us that this stained glass window is made up of little squares that's all 5 by 5 by 5. All right, but unfortunately that doesn't help us find this distance, because this distance is the diagonal of that. Well, wait a minute. They just told us here that each of those diagonals is 5 times the square root of 2. The diagonal of a square with side x, 5 in our case, is 5 times the square root of 2. All right, so this is 5 square root of 2. All right, so let's look at how long this side is. All right, well, let's not, we got this little half diagonal here, okay, and sorry, this came off really dark, so hopefully it prints off better for you. But let's look at, let's just go right down here. Yeah, we will go down here. So here's 5 square root of 2. There's 10 square root of 2. There's another 5. There's another 5. There's another 5. 1, 2, 3, 4, 5. 5 square root of 2's. All right, 5 square root of 2 plus 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 5 square root of 2. That's 25 times the square root of 2. That distance is, because really what we're doing is 5 square root of 2 plus 5 square root of 2 plus 5 square root of 2. All right, so on and so forth. Now, what about a side? Well, let's look here. I'm going to go right across here, and I've got 3 of the diagonals. So that must be 5, 10. That's 15 square root of 2. And let's see, this side is also 25 times the square root of 2. This side is also 15 times the square root of 2. So if I want to add all these up, because that's what I want to find is the perimeter, I add all these up, and they are like radicals, so I can do this. So all I got to do is add the coefficients, let's call them. So 25 plus 25 is 50. 15 plus 15 is 30. So that is 50 plus 30. The perimeter of this thing must be 80 times the square root of 2 inches. Now, that's a perfectly good answer. That's the exact answer, but they did ask for it to the nearest tenth of an inch. All right, so I'm simply going to get my calculator, and I'm going to type in 80 times the square root of 2 and get about what they want, tenth of an inch, 113.1. All right, so the perimeter of this thing is 113.1 inches. All right, so just a little application problem there, and recognizing, hey, if we've got this distance, we've got that distance, we want that vertical distance and that horizontal distance there. Okay, now I know what you're asking, and I'm ready to give you the answer. Or maybe you weren't asking this, but I'm going to give you the answer anyway. What do we do? All right, so let's take a look at this one. It says, what's the simplest form of the expression square root of 12 plus the square root of 75 minus the square root of 3? And you say, yay, we don't have to do anything because they're not like radicals. Wait a minute. What if we look at simplifying these before we add or subtract them? All right, so in other words, square root of 12, how can we simplify that? Well, let's see. Remember, we're looking for factors of 12 that are perfect squares. I'll give you a minute. 4. All right, so this is 4 times 3. So that would be the square root of 4 times 3. What about 75? 75, does it have any factors that are perfect squares? Yep, I heard you. 25 times 3, so I can write that as 25 times 3. Minus, and now 3. Does it have any factors that are perfect squares? No. All right, so that's just going to be the square root of 3. But now if we look at simplifying these, again, I could rip this up into 2. That'd be the square root of 4 times the square root of 3, and the square root of 4 is 2. So that would be 2 times the square root of 3 plus, that'd be the square root of 25 times the square root of 3. That's 5 square root of 3. And then minus, and here's the thing you got to catch, just like with variables, there's that understood 1 in front of there. So I'm going to write that as 1 square root of 3. And so now we've got 2. Oh, now look, all of a sudden, now that we've got it simplified, they actually are like radicals. So 2 square root of 3 plus 5 square root of 3 would be 7 times the square root of 3 minus 1. My simplified answer here would be 6 times the square root of 3. So sometimes what aren't like radicals actually do work out okay if you simplify them. All right. And just real quickly, why didn't we do that back here? Because these were already simplified. I can't think of any factors of 7 that are perfect squares. I can't think of any factors of 5 that are perfect squares. So that's why we didn't talk about that then. Okay. All right. Just one last example here. Now these are cube roots. All right. So let's see if we can simplify them. And again, remember, I would have that list. Let's get that list of perfect cubes here. Because we want to find a factor of 250 that is a perfect cube. So 2 cubed, 2 times 2 times 2 is 8. Will 8 go into 250? I don't think it will. All right. Let's look at the next one. 3 cubed is 3 times 3 times 3. That's 27. Will 27 go into 250? No. Let's see. All right. 4 cubed is 64. I don't think 64. Maybe this one can't be done. Let's check 5 cubed. 5 times 5 times 5. 125. All right. So I can write that. I'm going to write a little bit bigger out here. That's the cube root of 125 times 2. Now, what about 54? All right. Let's see. Ding, 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 ding. Okay. 54 is 27 times 2. So I can write that as the cube root of 27 times 2. Minus, and now what about 16? Oh, yep, right there. All right. So that's the cube root of 8 times 2. Again, just real quickly, a lot of different factors of 54. You can say, why didn't we do 9 times 6? Because neither 9 nor 6 is a perfect cube. We're looking for factors that are perfect cubes. That's why I chose 27 and 2. And so now we look at this. The cube root of 125 is 5. So that would be 5 times the cube root of 2. This would be the cube root of 27 is 3. So that would be 3 times the cube root of 2 minus, and the cube root of 8 is 2. That's 2 times the cube root of 2. And now they are like radicals. Same radicand, same index. We should be good. 5 plus 3 is 8. Minus 2 is 6. So it's 6 times the cube root of 2. Okay. All right. So looking at adding and subtracting these radicals, you can only add or subtract them if they are like radicals. All right. And sometimes they are going to be like radicals, and you simply add or subtract those coefficients. If they're not, maybe simplify them and see if they do come out to be like radicals. All right. So again, I want you to look at page 378, take a look at those problems. Don't share those through Flipgrid yet, because next week we're going to be looking at the second part of this, and there we're going to be looking at how do we multiply and divide radical expressions. So, but this should get you a start here. I'll still be posting these answers, and you can still check them, but you won't see a place to put those on Flipgrid, at least not yet, until we get to that second part. All right. So good luck with this. If you have any questions, let me know. Take care.